The following is a production of Texas Lutheran University. For more information, please visit tlu.edu.
Physics department's pleased to introduce our speaker for today, coming to us from Indiana University. Dr. Pilachowski is here as part of the Harlow Shapley lecture series from the American Astronomical Society, which is intended to bring public lectures to areas of the country that maybe don't have their own large astronomy department. So she's a endowed professor at Indiana University, a former president of the American Astronomical Society, and a well-known researcher in this area. So I'm pleased to introduce Dr. Pilachowski.
Thanks very much, Lee. As I said last night, it's a real pleasure to be here. I've enjoyed my visit a lot. It's been great to meet all of you, at least those of you whom I have met, and it's just been fun. I haven't been to this part of Texas before, so it's been a real treat, and I appreciate the opportunity to come down. I spoke last night about globular star clusters and the role that they play in helping us answer a lot of fundamental questions about the universe we live in. But I want to speak today more specifically about one globular cluster on which we've done a lot of work in the last couple of years. It's a pretty amazing thing as a cluster. It's unique in the galaxy. I don't know if it's unique in the universe, but it gives us a lot of pretty amazing insight into the process of chemical evolution, where the elements come from, and how complex the process can be to yield the kinds of abundance distributions that we find for the various elements in the periodic table. So I want to share with you what we know about Omega Centauri, and then also share with you some of what we think we know about Omega Centauri. As I mentioned last night, it's a naked eye object. It was known to the ancients, and I've circled it here in this diagram. Right here is Omega Centauri. From your perspective, it looks pretty much like a star, and it did to the ancients as well. For those of you not familiar with the southern sky, we have here Alpha and Beta Centauri and the Southern Cross. So it's really a pretty straightforward thing to find. But if you look at it in a small telescope, you see something quite different. It's really an amazing sight to suddenly see that object become 1,000,000 stars. It's just really pretty astounding. And I guess, in fact, it's visible from here. The latitude is not quite 30 degrees, and the declination of Omega Centauri is about -47, so a couple of degrees above the horizon, and on a good night with a good southern horizon, you might be able to actually make it out. I think it'd be a challenge, but it might be doable. Anyway, it's pretty cool to see in a telescope. Omega Centauri is just one of about 200 globular clusters that I spoke about last night in the Milky Way. These objects typically have 100,000 stars, some fewer, some like Omega Centauri are many more. They're all old, at least all of the ones in our galaxy are very old. They date from the formation of the galaxy itself, and so they really are fossils that tell us something about what our part of the universe was like within 1 billion years after the Big Bang. Most globular clusters are pretty uniform from one star to the other within the cluster in their metal abundance. They have mostly pretty similar, there are exceptions, but mostly pretty similar chemical compositions within one cluster. And that's sort of what you'd expect if all of the stars formed at the same time from the same cloud of gas, that you wouldn't expect to see a big diversity or big range in the chemical composition of the individual stars within a cluster. But they do span a fairly wide range of metal abundance, and I'm going to tell you about this scale in just a minute. But these globular clusters span a range of about a factor of 100 in the relative abundance of iron compared to hydrogen in the clusters themselves. So there's some very metal poor ones. There's a peak here that's at a sort of intermediate metallicity of around about 1/40th of the solar iron abundance. And then a second peak that's about 1/4 or so of the solar iron abundance. So there's some not so metal poor clusters and a whole bunch of very metal poor clusters. So they span a range, and that's indicative of the overall chemical evolution within the Milky Way in its earliest 1 billion years. The chemical evolution happened very quickly. You go from no metals to some metals very rapidly. It doesn't take a lot of iron to change the chemical composition from nothing to a tiny bit. And these two populations, the really metal poor ones and the not so metal poor ones, are part of two globular cluster systems in the Milky Way that I spoke about last night. I want to talk for just a moment also about the notation that I'm going to use fairly consistently through this talk today. It's the notation we use to describe the chemical composition of things in the universe that we astronomers use. Others use different kinds of notation, but we use logarithmic notation, and we use it for a couple of reasons. One is that we're spanning generally a fairly large range when we talk about numbers, and if we want to compare things over a fairly wide range, then logarithms give us a better opportunity to understand the comparisons and relationships better. And also because it's really hard to measure the chemical composition of something that is 10,000 light years away. And so we have a fairly large uncertainty in our measurements. If we use the logarithm, that uncertainty looks a lot smaller. And so factor of 2 seems small in the log, but it looks like it's pretty big in real life, in real numbers. So using logarithmic notation actually, I don't know, makes me feel better about the work I do. So what we do is compare the relative number of atoms of iron to the number of atoms of hydrogen, that ratio, iron to hydrogen, in a star compared to that same ratio in the sun. So we're really taking a ratio of ratios, and we're taking the log of that ratio of ratios. So if I use the notation Fe on H equals 0, that means that this ratio is 1. That means that the number of iron atoms to hydrogen atoms is the same in whatever star I'm talking about as it is in the sun. If Fe on H is -1, that means that there is only 1/10 the number of iron atoms per hydrogen atom that we're talking about. So that would say that that particular star got 1/10 the metallicity, or 1/10 of the iron abundance of perhaps the sun. And I'm also going to compare not just element to hydrogen, but also element to iron. That is, how does, say, the ratio of the number of calcium atoms to the number of iron atoms in a star, how does that compare to that ratio in the sun? Is calcium over or underabundant relative to that same ratio in the sun? And so I'm going to be talking about element to iron ratios, which can be expressed in the same way as that basically a difference in logs or a log of a ratio of ratios. So I'm going to use this kind of notation pretty consistently through. And you'll see a lot of that as we go through. All right, so omega Cent in particular, I wanted to share with you a little bit about its basic parameters. It's up in the sky now. This is a good time to go find it if you're far enough south. Its distance is about 5,000 parsecs, or about roughly 15,000 light years. It's visually pretty bright. It's a third, fourth magnitude star in the sky. So it's actually very easy to see with the naked eye. And its apparent size, just angular size in the sky, is about 36 arc minutes. That's the full size. The bright central core is smaller than that. But 36 arc minutes is not so different than the basic size of the full moon. So it actually spans a fairly large patch of sky. It's also known as NGC 5139, which nobody cares about. It is the brightest, biggest, most massive globular cluster in the Milky Way. It is located not so far from the galactic center. So it's about 6 kiloparsecs from the galactic center. We are 8 kiloparsecs from the galactic center. And it's located in a direction sort of toward the galactic center from us and a little bit off of the galactic center. Not exactly in the plane, but a bit off at plus 14 degrees from the center of the galactic plane. It's not perfectly round, and that's because there may be some bulk rotation to the cluster so that it's elongated a little bit in one direction, squished a little bit in the other direction. And it's in a retrograde orbit. That means it orbits the center of the Milky Way in the opposite direction from the bulk of the stars in the disk. There are stars, basically all stars in the disk, all go around in the same direction. In the halo, of which omega Cent is a part, stars tend to have more random orbits. They're not all going in the same direction. But most globular clusters are, in fact, orbiting mostly in the same direction as the sun. But omega Cent goes backwards. goes around the Milky Way in the opposite direction. Now, I spoke a bit last night about the color magnitude diagrams that we use for analyzing stars in clusters, and I wanted to start with this one today. This is the color magnitude diagram for the globular cluster Messier 5. And I selected it because it's a pretty diagram, but also because it's one of the better ones that have been done. It's very precise photometry. And we basically here are plotting the brightness of stars, and this is in an absolute magnitude scale. So these are the really brightest stars in Messier 5. These are dimmer stars. The sun would be somewhere down around here if it were in this cluster, or actually more around here if it were in this cluster, about a magnitude of 5 or so. And we simply measure the brightness and color of every star and plot it on this diagram. We have blue stars on this side, red stars over here, and of course they make a pattern. This is the main sequence, stars that remain after 12, 13 billion years of evolution. We've lost completely the upper part of the main sequence. Those stars have all died in the interval. Stars that leave the main sequence at this point, at the main sequence turnoff, are running out of hydrogen in their cores. They become red giants for a little while. Eventually they ignite helium in their cores, and they fall down onto this region, which we call the horizontal branch, mostly because it's pretty horizontal in this diagram, although clearly not everywhere is it horizontal. These stars happily burn helium in their cores for about 1 billion years. Eventually they run out of helium and they go into more exotic internal structures where they burn both hydrogen and helium in shells around a central carbon-oxygen core. And they occupy this region that we call the asymptotic giant branch for a short period of time before they lose their outer atmospheres and evolve off over the top of this color magnitude diagram and way down here, down, you can't see, but down on the floor, to become white dwarf stars. And all of these stars will eventually become white dwarfs when this cluster is old and dead. But in the meantime, I want to turn to the color magnitude diagram for my favorite cluster, Omega Centauri. And if you just recall how skinny this one looks here on its red giant branch, and then look at Omega Cen, you can see why this cluster is interesting, because it's just really different. There are a lot of differences between this one and M5. One is that it's got an interesting main sequence, which I'll show you in a minute. It's got a fairly wide turnoff. It's got a whole huge range of stars on the red giant branch and a messed up asymptotic giant branch. And then it's got this horizontal branch. This is anything but horizontal. That we have down here, these extreme blue horizontal branch stars that we don't see in most globular clusters, but we see a lot of in Omega Centauri. These with the little square dots are variable stars. They're pulsating RL-Iris stars in the cluster. Omega Cen has a lot of those. But really what is most compelling is this huge swath of stars on the red giant branch and this very, very extended turnoff region in the cluster, which tells us automatically that there's something very different happening in Omega Cen than we see in all of the other clusters. And what is happening in this cluster is, in fact, multiple epochs of star formation. In a typical globular cluster, stars formed pretty much once. But in Omega Cen, stars formed over and over and over again in a very episodic kind of pattern. And it wasn't a continuous process of star formation, but it truly was episodic. There were repeated bursts of star formation that made individual, separate populations of stars in the cluster. And as we look at this diagram, you can see traced out on these colored lines for different isochrones, that is, lines of constant age, showing for different initial properties where the stars would be. And these are for isochrones of 4 different metal abundances, showing a very metal-rich isochrone for what would happen if stars were quite metal-rich, and then an isochrone for metal-poor stars, showing in the main sequence turn-off, subgiant branch, and giant branch. So you can see automatically, as we just look at these isochrones, that the range of luminosity and color that we see in the giants in Omega Centauri can pretty well be explained by just saying there's a range of composition amongst stars in this cluster. They're not all the same composition. It's a mixture of different metal abundances, and that produces this very large spread in the giant branch. But let's look more closely at it. Here is a preliminary metallicity distribution function showing what the metallicity of stars in Omega Cyn is. So we have a few really metal-poor stars, down by about a factor of 100 in iron compared to hydrogen compared to the sun, a whole lot of stars with intermediate metallicities, a bunch with not quite so metal-poor, and then a long tail of stars that go to relatively high metallicities, up to something like about a quarter of the iron abundance compared to hydrogen in the sun. So we see this range, and from these data alone, you wouldn't say they're episodic events of composition, but I wanted to compare just to show you what a typical cluster's metallicity distribution function would look like, and that is this one for Messier 12, which is cut off, but you can trust me, it is, which is basically monometallic. This little tail is only a result of binning in how I plotted the data. But basically, all the clusters have the same iron abundance in this cluster. All the stars have the same iron abundance, unlike Omega Cyn, where we have this huge range of iron abundance. But Omega Cyn is even more surprising. When we look very closely at its main sequence using photometry from the Advanced Chemical Surveys on the Hubble Space Telescope, we detect, and in fact, this is just a small fraction of the stars. Otherwise, this diagram would be just covered with stars. But there's the main sequence of Omega Cyn is here, and there's a second parallel main sequence just to the left of it. And these stars are indicated with color, red stars and blue stars, because those were observed spectroscopically with the very large telescope run by the ESO Southern Observatory in Chile. And it turns out that these red stars are more metal poor than these blue stars. And that's very, very odd, because normally when we look at isochrones of different metal abundance for the main sequence, if a star has lower metallicity, it generally lands to the left of the normal composition main sequence. And so the fact that these stars are to the left but more metal rich makes no sense at all, unless we look at the helium abundance. And it turns out, although we cannot measure the helium abundance in these stars because there are no atomic transitions of helium that show up in stars of this temperature, if we theoretically increase the amount of helium and look at its effect on the main sequence, or where stars are on the main sequence, if we increase the amount of helium in these stars by 50% compared to the canonical cosmic value, then we can account for this odd main sequence. So the hypothesis would be that these stars result from a population of stars that has very, very high helium abundance. 50% higher than the sun, 50% higher than the Big Bang, really quite an unusual abundance of helium and completely unexpected and unaccounted for. So big question is, where did the helium come from? Omega Cyn isn't finished with surprising us, because if we look even harder at its main sequence, we can see the blue main sequence here and the normal red main sequence here. They kind of merge up here at the top. And then there's another one right here, a faint, low population red main sequence. So Omega Cyn has at least 3 main sequence populations, indicating 3 epochs, at least 3 epochs of star formation, and with different basic compositions and ages to explain these different main sequences appearing. So we call the one on the red side MSA, which is the reddest main sequence. The RMS for red main sequence is the main one, and the BMS, the blue main sequence, on the left side here. And I'm going to come back to those later, so keep these in mind. Here is a more extended diagram showing all of the stars included in the ACS survey with Hubble. And you can see, looking here at the turnoff region, the subgiant branch region, you can see 1, 2, 3, 4, 5 perhaps different lines of stars running through in that region, indicating there may be not just 3 populations of stars in Omega Cen, but many populations, maybe as many as 5 different subpopulations. And in fact, a detailed statistical analysis of the various kinds of ways of looking at these data suggests there may be as many as 7 populations, different populations of stars within the cluster. We can easily track the red main sequence up to produce the very red giants that we see up here. And we can track the main sequence, that's kind of redundant, up that produces the blue side of the giant branch here. But in between, these other populations get all messed up, both at the turnoff region and up here in the giant branch region. And it's very hard to separate what star belongs to what track, going all the way through from the main sequence up to the giant branch. If we look just at the region of the subgiant branch here, just after the main sequence turnoff, we can produce, cutting across at an appropriate angle, we can produce a distribution function of what likely is mostly metallicity, which shows some of the very complicated structure that we see in the cluster. So there are clearly multiple populations here, and more populations than just the 3 that we can easily identify from the main sequence photometry itself. There's another surprise even waiting for us in the center of Omega Centauri, and that is when we look at the very central part of the cluster. This is an image of the central part of the cluster taken pretty much with adaptive optics, or maybe the ACS image, I'm not sure. And this is a ground-based image. There's a little square here, and that square is replicated here, and you can sort of see the same pattern of stars. Each of these little teeny hexagons in that pattern is a separate aperture into what's called an integral field spectrograph that allows us to measure or get the spectrum of each separate region of that central core in Omega Centauri. And here are some reproductions of the spectra that are obtained from these different parts of the image, looking at lines, very strong lines of calcium in the near-infrared part of the spectrum. Here's a blow-up of one of the lines. We're basically going to be looking at the width of these features from different regions of this central core. And the width of this feature is tied into the velocity dispersion. That is, what is the range of velocities that are contributing to the integrated spectrum that we see from each spot in this image. There are a whole lot of stars contributing in each of those spots in the image. We get an integrated spectrum, and it's broadened because all of the stars contributing are moving at different velocities. So what I want to show you is a plot of the velocity dispersion here on the y-axis, ranging from 5 kilometers per second up to 30 kilometers per second, as a function of distance from the center of Omega Centauri. And we see, as we go out from about 3 to 4 arc seconds away from the center, the velocity dispersion is increasing. You expect that because as you go in, just through Kepler's laws, the stars are moving faster. But as we go in even further, and here we go in at 10 arc seconds, and here we begin to get the velocity dispersions from the data here in the central 10 arc seconds of the cluster, the velocity dispersion continues to rise pretty dramatically as we go toward the center. Now, the models that are fit through these data are models that hypothesize that the center of Omega Centauri contains a black hole of a few thousand, ranging from 10 to the fourth, so 10,000 solar masses, up to 7.5 times 10 to the fourth solar masses. And what that indicates, the best fit models suggest that the black hole at the center of Omega Centauri has a mass of about 40,000 solar masses. This is the only globular cluster that we know of in the Milky Way that harbors a globular cluster, or harbors a black hole, but there does appear to be one at the center of Omega Cen. We know of 2 or 3 other globular clusters in other galaxies, 1 or 2, for example, around the Andromeda galaxy, that also appear to have black holes in their centers. But in our galaxy, Omega Cen seems to be the only one. And its black hole mass is very consistent with the general run of black hole masses for galaxies. So it's typically the case that we can look at the mass of the sort of the spheroidal, the bulge component of a galaxy, and plot that versus the mass, measured mass of a black hole at the center of a galaxy, which we can get from the velocity dispersion. And there's a pretty good correlation. The bigger the galaxy, the bigger the black hole mass. And omega Cen falls pretty much right here, right on that correlation. And that is the first indication, or at least a partial indication, that omega Cen may have more in common with galaxies than it does with globular clusters in the Milky Way. So omega Cen turns out to be surprising for a lot of reasons. It's got multiple main sequences, multiple stellar populations, a big range of metal abundance. It has a black hole in its center. So there's a lot going on with Omega Centauri. Because of all of those interesting things happening in the cluster, one of my former graduate students, Christian Johnson, who was an undergraduate at UT Austin, who came to Bloomington for his graduate work, and who is now, he's from Houston actually, not so far away, and is now a postdoc at UCLA on an NSF postdoctoral fellowship. He undertook for his dissertation to measure the compositions of 855 giants in Omega Centauri. So the red dots are all the stars he analyzed. This young man worked incredibly hard. He analyzes a star faster than anyone I have ever known. But he did all of these stars. It's almost a complete sample of all of the giants in Omega Centauri. Anything above, brighter than about magnitude 13.5, he got a spectrum and did the analysis. And it's just an astounding body of work. And it tells us a great deal about the origin and history of Omega Cen. Here's an example of his spectra. He was focusing primarily on measurements of the abundance of sodium using these two lines at 6154 and 6162 angstroms. But you can see other features of silicon, iron, calcium here in the spectrum. Mostly the stars agree pretty well, but the sodium lines don't agree. Silicon's a little off as well in this case. Here are two lines of aluminum. The red and blue lines are two different stars in the cluster. And you can see the iron lines are very similar. The cobalt lines are very similar. Nickel is very similar. But aluminum is really different between these two stars. And here is an example of two stars. Cobalt, nickel, iron all look sort of similar, and lanthanum is quite different. Now, I love talking about Omega Cen in a lecture hall with a periodic table because I can point out where some of these elements are. So I'm sure you know where sodium is, and aluminum, where did it go? Right here. These are light elements, and I'm going to talk about their origin in a bit, but I also want to mention lanthanum, which is down here, element 57. In different regions of the periodic table, elements are produced by different processes, and the differences between sodium, aluminum, oxygen, iron, lanthanum, calcium are things that we're going to talk about over the next few minutes. The first thing, of course, that we pull out of all of this spectrum analysis is the metallicity distribution function for iron in the cluster, and we see the main metal pore population was highly represented. This is the blue population here. And then there is a green intermediate red giant branch population, and there are actually 3 of them that are noted from various different studies that occupy the stars in this central region. And it's very hard, without detailed metal abundances, to pick out which star is in which of these populations. I'll get to more of that in a minute. And then this RGB-A population, which evolves from the main sequence A population, the red side main sequence. And so we get a good metallicity distribution function. This is probably the best one produced for the cluster. And we're able to categorize what the relative populations of stars are in each of these populations, compare back to the main sequence, compare back to the distribution function from the subgiant branch, and then are able to sort of tie these populations together in a way that makes actually some sense. Now, before I begin to interpret all of those data, I want to give you a very short lesson on nucleosynthesis, on the origin of chemical elements in stars. And there are basically 2 sources that are important for most of the elements. They are, or let me say 3 sources: the type 2 supernovae, the type 1a supernovae, and then intermediate mass and low mass asymptotic giant branch stars. Remember I pointed out the asymptotic giant branch stars on the M5 color magnitude diagram. These are stars that have depleted core hydrogen, they've depleted core helium, they have carbon-oxygen cores, and they have this double shell hydrogen-helium burning going on in outer layers, and then an envelope of hydrogen around them. And interesting things happen in that situation that produce a variety of opportunities for nucleosynthesis. But let's talk first about the supernovae. Type 2 supernovae are massive stars that come to the end of their nuclear fusion and basically implode and then explode. In the process of that implosion and explosion, they produce very large amounts of iron in explosive nucleosynthesis, and they produce excesses of oxygen and the alpha process elements, elements that are produced by adding helium onto things. Add helium onto carbon, you get oxygen. Add helium onto oxygen, you get the next even number going up the periodic table, on up through about calcium. So the type 2 supernovae and that sort of explosion produce iron peak elements, that is the iron peak across here, up through about copper. They produce calcium, as well as argon, sulfur, silicon, magnesium, neon, and oxygen. They produce the odd Z light elements. That would be aluminum, phosphorus, chlorine, etc. And they produce those through explosive nucleosynthesis. And then if we look just at the lower mass, in the 8 to 11 solar mass range of supernova explosions, they produce what are called the R process elements. The R process elements are basically everything heavier than about zinc in the periodic table in various proportions. They're produced by neutron capture processes, and we'll talk more about neutron capture processes in a few minutes. But many of these heavy elements are produced in these exploding, relatively low mass supernova explosions. Type 1a supernovae are carbon-oxygen white dwarf cores which have exceeded the Chandrasekhar mass limit. And these cores basically undergo sudden fusion of carbon and oxygen. They suddenly get sufficiently high temperature because they've exceeded a mass limit. The electron pressure collapses, the material collapses, and it gets high enough temperature and density that carbon and oxygen begin to fuse, and they blow the thing apart. And those type 1a supernovae produce huge amounts of iron, but they produce calcium to iron ratios that are just like the sun. These type 2 supernovae produce excess calcium and excess oxygen, more calcium and oxygen per iron atom than we have in the sun. So in the sun, most of our material actually comes from type 1a supernovae. But as we'll see in early stellar populations, it's the type 2 supernovae that make the largest contribution. And then the intermediate mass AGB stars don't have sufficient central temperature and density to do a lot of nucleosynthesis, but they do some. And what they do is through two processes. In the intermediate mass ones, they undergo proton capture nucleosynthesis. I'll show you a bit more about that in a minute. But for those of you who have studied some astronomy, the process you're probably most familiar with that's proton capture nucleosynthesis is the CNO cycle, where carbon captures a proton and it goes through a series of proton captures, serving as a catalyst and eventually converting protons into helium and returning back to carbon-12. It's a whole cyclic process. And there are other such similar cyclic processes that can occur in intermediate mass AGB stars that we will see evidence for in Omega Centauri. These stars produce very little neutron capture process elements through another neutron capture process called the S process. But low mass AGB stars, stars like the sun, can produce substantial amounts of certain of these heavy elements. And so these basic sources, the supernovae of type 2, the supernovae of type 1a, and the intermediate mass and low mass AGB stars are really the characters responsible for a lot of the nucleosynthesis that we see in the galaxy and in Omega Cen. So I can code up the color or the periodic table to show you the proton capture elements, which are carbon, nitrogen, fluorine, aluminum, sodium, the alpha and magnesium partly, silicon partly, sulfur partly. The alpha process elements, which I've already named, are the odd or even numbered elements. The iron peak elements here, and then a bunch of neutron capture elements that we want to talk about in a bit more detail, about where they come from. The proton capture process is very complicated. In ordinary stars, a little bit more massive than the sun, maybe even some of the time in the sun itself, we see the CNO cycle of proton capture going on. But in more massive stars, where the temperatures are higher and the densities are higher, we also get proton capture on neon and sodium. Also a loop that goes back to the original neon, but in the process changes the distribution of amounts of these different isotopes. And likewise, the magnesium-aluminum cycle that takes an even higher temperature, and one that involves silicon that takes yet an even higher temperature still. And what these cycles do is redistribute material. An abundant element like neon becomes a little bit depleted, and it dramatically increases the amount of a less abundant element, like sodium, for example. So we rearrange the abundance of these species through proton capture nucleosynthesis, which we will see in just a moment in Omega Centauri. So here are the results we get from analyzing 855 giants in Omega Centauri. And again, I've color-coded the different types of processes that we want to talk about, and then shown the actual data that we've gotten. The simplest ones to look at are the basic metals. So nickel, for example, titanium, scandium, all are very nicely behaved. What I've plotted here is the relative element to iron fraction, element to iron, versus the iron abundance. So here are the metal poorest stars, the least metal poor stars, and the dashed line is the solar element to iron ratio. So we're seeing here that the stars don't differ very much from the solar ratio for scandium, titanium, and nickel, all elements here in the iron group. But if we look at oxygen or sodium or aluminum, we see something quite different, that we see stars with extremely low oxygen to iron ratios, stars with extremely high sodium to iron ratios, stars with very high aluminum to iron ratios. We see on the S or the alpha process elements, these are the helium capture elements, we see excesses of silicon, excesses of calcium compared to the solar composition. And the heavy elements, lanthanum shows an extreme amount of processing, showing very high heavy element abundances in a lot of stars, although europium does not. So we see a lot of interesting things going on in Omega Cen in looking at the chemical composition of the cluster and what it tells us about nucleosynthesis. So what we want to do is understand where are the elements coming from, what kinds of processes are producing the chemical mixtures in the stars that we see in Omega Centauri. The first thing we want to look at is supernovae and what are they contributing to the chemical mixture. So here is a reproduction of the oxygen plot. Again, it's the oxygen to iron ratio versus the metal abundance, the iron abundance in the cluster, metal poor, less metal poor. And we can see the bulk of the stars show an excess of oxygen, but there are a lot of stars that show a strong deficiency of oxygen in the cluster. The blue line is the expected yield for type 2 supernovae, and the red line is the expected yield for type 1a supernovae. So we can account for the bulk of the stars as having had their materials produced in type 2 early generation stars in the cluster, massive stars that produce type 2 supernovae. But the important thing is that we cannot account for the oxygen poor stars through supernova production. Some other kind of process has to be making the stars, or the elements in the stars, to account for this very low oxygen abundance that we see. Sodium, we really can't account for the sodium abundances at all with the supernova yields, either type 1 or type 2. Likewise with aluminum, we have a huge excess of aluminum. That's almost or about a factor of 10 excess in the aluminum to iron ratio. And we can't account for it certainly with type 1a and not even with type 2 supernovae. Calcium, it sets an important limit for us. We can account for the calcium abundance all the way from the most metal poor stars to the most metal rich stars as production from type 2 supernovae. but we do not see very few at least, very few low calcium stars that would indicate significant contribution from type 1a supernovae, the exploding carbon-oxygen white dwarfs. And so we can pretty much rule out, based on the calcium abundances, that the type 1a supernovae made any kind of significant contribution to the chemical mixture that we see in Omega Centauri. When we look at the oxygen, the sodium, and aluminum in more detail, we find we can, in fact, account for most of those abundances by looking at the yields of the 5 and 6 solar mass asymptotic giant branch stars. They took their elements that they were born with from the previous supernova generation, processed those elements, threw them back out into the proto or early cluster, and that ejected material was used to form new stars, which are the stars that we're seeing here. And if we look closely at the various yields that we get from type 2 supernovae, the blue line, versus different mass ranges of these asymptotic giant branch stars, we can see that the oxygen abundances that we find in Omega Cen can be produced in AGB stars of around 6 solar masses. Likewise, the sodium abundances, the very high sodium abundances we can produce with AGB stars of a variety of solar masses, not type 2 supernovae, and not all of the mass ranges, but we can account for the abundances of sodium that we see from these AGB stars. And likewise, the aluminum abundances that we see, we can account for by relatively high mass, intermediate mass asymptotic giant branch stars. And you see how, as we get to higher metallicity, the production of aluminum drops off, rather nicely matching the models. And so we know that this population of stars that we see with low oxygen, high sodium, and high aluminum seem to arise from stars that are made virtually purely from the ejecta of intermediate mass stars. They're not made from the ejecta of supernovae, but rather from the ejecta of these intermediate mass stars. One would expect the ejecta of intermediate mass stars to be rich in helium, because if they're intermediate mass stars, they've seen a lot of processing of their outer envelopes. If we see this kind of excess of sodium and aluminum, we would expect also to see a lot of protons being converted into helium, into alpha particle nuclei. And so it's very difficult to make measurements of helium abundance in stars, particularly in giants, because there really aren't transitions that are formed in the photospheres of these stars for helium. However, the stars do have chromospheres, and in the chromospheres there is an additional amount of heat transfer that is not radiative transfer that causes the chromospheres to be rather hot. And there is a line of helium at 10,830 angstroms in the infrared, which is not easily used for an abundance measurement because its formation isn't through simple radiative transfer. But it nonetheless is detectable in the spectrum. Oops, and these are measurements of the strength, excuse me. These are measurements of the abundance of aluminum versus the abundance of sodium from our observations. High aluminum stars, high sodium stars are here, low aluminum, low sodium stars are here. Andrew Dupre at Harvard Observatory used a spectrograph on the Gemini South Telescope to measure the strength of the 10830 helium line in a variety of Omega Cen giants, and she found that the high sodium, high aluminum stars are, for the most part, rich in helium. They have strong 10830 lines. Even though it doesn't indicate the abundance, the fact that it's there at all means that there has to be a high helium abundance. So this is confirmation both that the blue main sequence is in fact high helium, and that those stars are the progenitors of the sodium aluminum rich giants that we see on the upper giant branch. And so this whole picture begins to hold together that in fact we have a high helium population, and that population is made from gas, which was the ejecta of earlier generation of asymptotic giant branch stars. Let me turn for just a quick moment to the neutron capture processes. That is how we make all the rest of these elements in the periodic table. There are basically two kinds of ways to make these heavy elements through neutron capture. One is that the two processes depend on the flux of neutrons. If the flux is low, then a heavy element or heavy nucleus like iron or platinum or hafnium can absorb a neutron. And often when that happens, when a neutron is absorbed, the resulting nucleus is unstable, and it will beta decay. And if the flux is low enough, the element will beta decay before it captures another neutron. And if that's the case, then we see the formation of particular isotopes going up following this green line. That there'll be neutron capture, neutron capture, neutron capture, neutron capture on xenon, for example. It'll get to an unstable nucleus, beta decay to a cesium nucleus, capture a neutron, beta decay to barium, and then it can capture more neutrons. And it will follow and produce only these elements. So for example, the slow process will not produce barium-130 or barium-132 because there's no way for the neutrons the atoms to get there because of the decay process. And then there is a rapid process. If the neutron flux is extremely high, if the nucleus doesn't have time to beta decay before another neutron is captured, then the nucleus simply captures a ton of neutrons and then beta decays all the way back to the valley of beta stability in the chart of the nuclides. And that will produce certain of these species, but not produce other species because others will be blocked by stable nuclei. And so we end up with a different pattern of abundances for these two processes. Some produce lots of some elements, others produce lots of other elements. And in fact, of the two elements that we're able to observe in our omega Cen subset, we have lanthanum, which is produced by the slow process of nucleosynthesis, and europium, which is produced by the rich or rapid process of nucleosynthesis. We see basically a flat distribution of the europium to iron ratio. Europium is produced by type 2 supernovae, but not by the slow process that occurs in the AGB stars. Lanthanum is not produced in great abundance by type 2 supernovae, but is produced in AGB stars. And so this huge increase in the lanthanum abundance that we see in cluster stars is another indication of the contribution of these AGB stars into the chemical mixture of the cluster. Now, another factoid that I want to share with you about omega Cen is that its chemical composition is very different from other populations in the Milky Way. And I've included here the black dots are stars in the galactic disk. The purpley ones are, wherever they are, all scattered faint in there, this one, are metal poor halo stars. The green dots are bulge stars. There are just a handful of those in through here. The blue ones, the cyan ones, are dwarf spheroidals. Those are companion galaxies to the Milky Way. And the colored bars, the magenta things, are typical globular cluster abundances. And omega Cen's abundances are not anything like the red ones, anything like. Calcium's okay, but aluminum and sodium aren't anything like any other populations that we see in the Milky Way galaxy. And likewise, we see a dramatically high abundance of lanthanum, a lot of S-process contribution from AGB stars in omega Cen that we don't see in other populations in the Milky Way. And it's to some degree a weak amount of europium as well. So omega Cen is unique in its chemical evolution history. We know that roughly half of the stars are like stars in the halo in the thick disk of the Milky Way. And we do have some O-poor stars and these astounding sodium and aluminum rich stars. We have normal alpha process elements, and we can't explain all of this with just one type of nucleosynthesis process. So what are the clues that we have to the origin of Omega Centauri? I've covered a lot of things in a short amount of time. We have multiple stellar populations. We have contributions of both supernovae type 2 and AGB stars contributing to the chemical mixture of the various populations in Omega Cen. We see evidence of, but we don't see contributions from type 1a supernovae because the calcium to iron ratios don't seem to drop as they should if type 1a's were contributing. We see these anomalies in proton capture and S-process nucleosynthesis. We see that the enrichment occurred over some period of time because AGB stars take 1 billion years or so to evolve to the point where they make these kinds of nucleosynthesis contributions. And we see a unique chemical composition. So how do we explain the origin of Omega Centauri? Well, from various other observations, we can rule out, say, a chance alignment of 2 clusters in space or 5 clusters in space. It doesn't actually work. We can't explain it by merging clusters together for a variety of other observations. We can't reproduce what we see with that kind of approach. So the current hypothesis is that Omega Cen is actually the remnant of a small galaxy that was destroyed as it merged into the Milky Way. And Omega Cen is basically the remaining piece, identifiable piece of that galaxy, although it's now been possible to identify tidal streams from the disruption of the original galaxy, which originally hosted Omega Cen. So it turns out to be a pretty interesting object. We see alpha process elements from type 2 supernovae, proton-neutron capture. We know because of the gravitational potential of the cluster today is not sufficient. There's not enough mass in the cluster today to retain the products of supernova explosion, that when Omega Cen formed and went through its multiple phases of chemical evolution, it had to have been a lot more massive than it is today to retain the supernova products and even to retain the AGB star ejecta, which leave at a much lower velocity than supernova material does. So there must have been phases of Omega Cen's history. And we see a distinct shift in the chemical composition of Omega Cen that probably indicates the time at which it was captured within the tidal field of the Milky Way. So we can reconstruct a history of Omega Centauri from the chemical data and the kinematic data that we know about the cluster. We suspect that it probably formed separate from the Milky Way, not part of the Milky Way galaxy, but as part of its own small galaxy. It formed, and through the process of formation, there were type 2 supernovae that blew up, produced a lot of iron and calcium, that formed the first generations of stars in Omega Centauri. And those generations continued to form. Material continued to be retained. There were multiple episodes of triggered star formation that produced these multiple populations. But eventually, it seems that Omega Cen began to lose mass, and it began to lose the ability to retain supernova ejecta. But it didn't lose the ability to retain the ejecta of the AGB stars. So the low metallicity stars, the ones that were in the range of 6 or so solar masses, then evolved, became AGB stars, changed their compositions, spread their material out, blew it away from the central stars. New stars formed from the material that was ejected by these intermediate mass stars. And those new stars formed with the old iron abundance, but with the chemical signature of the AGB stars. And so we ended up with a relatively metal-poor population of stars, but which are formed from the ejecta of these intermediate mass processes. And so we get a complex picture for the formation of Omega Cen. There were multiple epochs of supernova ejected material that formed additional generations, followed by this generation of oxygen-poor stars with high helium, high sodium, high aluminum from the previous generation of the RGB INT1 stars. And eventually the interaction with the Milky Way did 2 things. It stripped away enough of the mass that the cluster could no longer retain the AGB star ejecta, which stopped star formation, and it became sufficiently tidally bound to the Milky Way that it began to pass through the disk of the Milky Way, which effectively stopped star formation by stripping the gas completely out of the cluster. And so for the first few billion years of its existence, Omega Cen acted in a very amazing way and produced an incredibly unusual population of stars. But because of its tidal interactions with the Milky Way, that process stopped. But it was exactly that tidal interaction that allowed Omega Cen to create this unusual population of aluminum, sodium-rich, oxygen-poor, helium-rich stars. So its unusual history really is revealed by understanding its chemical composition. Now, this is a fancy picture. I've tried to create a story for you that explains how Omega Cen came to produce the kinds of stars that we see with the element abundances that we have. But it's still a very preliminary picture. We still don't have observations of the main sequence stars, and we have a lot more to learn about Omega Cen. So I want to leave you with a cautionary note, and that is that time will tell whether this story actually makes sense or not. Thank you very much. Questions? Yeah.
The elemental abundance of the Earth, in particular, we've got an awful lot of aluminum. Does that mean that it can't have come from a supernova collision, that it has to come from something like this?
The actual abundance of aluminum in the Earth is pretty similar to the Sun, which is pretty similar to the bulk disk composition of the galaxy. So we see a lot of aluminum in the crust, but on average, the composition of the amount of aluminum in the Earth is pretty similar to,
It's just that it's
yeah,
all in the
yeah.
crust.
So a little of that aluminum came from AGB, but the bulk of the aluminum results from the explosive nucleosynthesis, proton capture nucleosynthesis in the supernova explosion.
So we're just plain
Yeah.
old supernova.
Plain old supernova, yeah. And in fact, the aluminum-26 abundances that have been detected in meteorites or former aluminum-26 abundances are an indication of that direct supernova action. Yeah.
What distinguishes a galaxy from a globular?
Good question. The one thing I didn't talk about is dark matter. So galaxies are dark matter dominated. That is, the majority of matter in the Milky Way galaxy and in every galaxy we've ever studied is dark matter. It's not stars, it's not gas, it's as yet undetected and unknown matter. The attention paid to the Higgs at the Large Hadron Collider may solve this problem, we hope. But in the Milky Way, there are several times more amount of dark matter than there is ordinary matter. But in star clusters, the amount of dark matter is zero, that it does not appear to be a dark matter cloud associated with any of these star clusters. So Omega Cen does not share that characteristic with other galaxies. And when we look at dwarf satellite galaxies of the Milky Way, for example, Draco or Canis, whatever, all of the little dwarf galaxies that surround the Milky Way, they are dark matter dominated. So Omega Cen is very different from those. But the processes by which you get tidal capture and tidal stripping may in fact cause the dark matter to basically get extended away from the cluster. And so we don't really know what happened to the dark matter. We don't understand why globulars don't have dark matter if they formed very early in the history of the Milky Way. But I have in my mind a picture. It's one of my favorite pictures, but you may not have seen it, so I'll describe it to you. Picture of the bullet cluster. Does that ring a bell with anybody? So this is a picture of two galaxy clusters in space, far, far away, that have collided. So they've passed through one another. And mostly clusters are open space. And so the galaxies just sort of pass right through. But most of the baryonic mass in clusters of galaxies is in fact hot hydrogen gas that's distributed in a very large volume all around the galaxy cluster. So when two galaxy clusters collide, the galaxies pass right through, but the gas gets stuck because the two gas clouds basically aren't, they collide. And so in this picture of the bullet cluster, you have two galaxy clusters with a big gas cloud right in between them. In that case, the dark matter follows the galaxies in passing right straight through, but the gas cloud gets separated. And that model may, in fact, explain why globular clusters don't have dark matter. And that is that if we're looking at a model of the early universe where we have many, many, many small galaxies forming, merging, colliding, they're going to get stripped of their gas. And that stripped out gas may be what ends up forming these globular clusters. So the early processes may, in fact, explain some of it, but nobody's worked that through yet. Yeah?
Have there been other clusters that kind of mirror this multi-train effect at all that you could use some comparisons?
Yes, but nothing to this extreme. So there are a handful of clusters, Messier 22, Messier 54, that have hints of this complexity in their chemical compositions. Messier 13, which is nearby, really bright, easy to see, also seems to show a population of stars that has unusual, not as extreme as omega Centauri, but unusual sodium and aluminum abundances. It seems to be typical of globular clusters that to a limited extreme, they go through some nucleosynthetic processes that produce a different generation of stars. But they tend to be very minor, whereas in omega Centauri, it was really over the top. So it's a pathological case that I think sheds light on how all clusters formed, but at a much less extreme level. All right, well, thank you very much.
Students at TLU engage in high-impact educational experiences that include civic engagement, aesthetic expression, critical thinking, and a focus on intercultural knowledge in a community that welcomes the interplay of faith and reason.